Okay, so we're going to look at the risk and benefits of using certain chemicals, and we're going to look at using that to obtain information from some data. One of the ways that we're going to do it is we're going to look at the LeBlanc process and look at the risks and the benefits to do with that. So if we just look at the LeBlanc process for a second. So I hope that you know that the LeBlanc process makes sodium carbonate, and that the chemical formula for sodium carbonate is Na2CO3. Notice that it's a capital N lowercase a. Sodium has two letters associated with it. Carbon and oxygen only have the one, which is why they are capital letters. The two major waste products that it makes are hydrogen chloride gas, HCl, the little g in brackets means gas, and the toxic foul smelling gas is hydrogen sulfide, is H2S gas. Okay. Hydrogen chloride may be oxidised to make chlorine gas, which has many applications. That process, just as a reminder, is the Deacon process. Okay. Chlorine is added to the water supplies. Why? Why would we add chlorine to water supplies? Well, it makes it cleaner. So it cleans it. And it cleans it by killing microorganisms and it removes some of the bad smells. Removes smells. What effect does it have on chlorinating water? What effect does chlorinating water have on disease rates? Well, if we're killing microorganisms, then we're going to reduce disease. But what are the risks of adding chlorine to water? Well, what happens if a leaf or something gets into the system? The chlorine can actually react with the organic material in the leaf. So, bad things happen when that occurs. You can get something called trihalomethanes, THMs. And THMs have been linked, but not proven, to cause cancer. There is some concern about it, but there's just not enough evidence at the moment to make it, to make the doctors and medical profession absolutely certain that they do absolutely cause cancer. Okay, so let's move on now to the use of other chemicals, also requiring us to weigh up risks and benefits. What are the plasticizers? Plasticizers are molecules that get added to a polymer to change its properties. And we've been asked to draw a diagram that represents a plasticizer in a plastic. So this then comes back to our nice wiggly line diagram. And we're going to draw some plasticizer molecules in here, where the wiggly lines are your polymer and the blobs are your plasticizer. Okay, brilliant. What properties of the plastic does the plasticizer alter? This goes back to C2. Well, it makes them softer and it makes them more flexible. One example then of a plasticizer use, is in PVC. Which three elements are found in PVC? Well, I'm hoping that you remember that your monomer for PVC PVC is chloroethene. Your repeating unit looks like that, which means that the answer to that question is carbon, hydrogen and chlorine. What are the main risks and concerns about using plasticizers in PVC? Well, it's mainly to do with the leaching. Okay, the leaching of plasticizer. The plasticizer itself can be quite dangerous. Okay, so plasticizers can be toxic, and we don't want them in our bodies. And then finally, reasonably related to that, some chemicals persist in the environment. What are they called, and what are the other uses of the risks of these chemicals? Chemicals that persist in the environment are called POP, persistent organic pollutants. Okay, POPs. Okay, and again, they have been linked to causing cancer due to accumulation, bioaccumulation, because they get stored in the fatty bits. Okay, right, so that's that, which is all well and good. So that's the Leblanc process. What then? How then do we use this information? How do we use information about risks and benefits? Well, what we've got here is we've got a graph. And you're told that this is a graph to show the incidence of typhoid in a city from 1910 to 1960. And the city began to chlorinate its water supply in 1920. And you need to describe and explain how the incidence of typhoid in the city changed from 1910 to 1960. Okay, so first of all, what information do we have? We've got information about 1920. 1920 is here. 1920 then is all the way up here. So we've got that spot there. So that's when they started chlorinating water. And we're going to describe and explain how the incidence of typhoid in the city changed from 1910 to 1960. Well, after here, we can quite clearly see that there's a definite trend downwards. Before there, it kind of wiggles about a bit, but generally, roughly flat. Okay. So how would we actually explain that? Well, if you were to look at the different areas of the graph, you might describe that there was little or no decline prior to 1920, or at least the level was consistent. The number of cases started to fall after 1920, or once chlorination was introduced, and that by 1960 there's almost 0 cases of typhoid. We're going to use the same similar thing to answer question 9 of this 2013 paper. And here we go. Okay, so typhoid is a disease that is passed on by infected water or food. The graph shows deaths in London from typhoid 1880 to 1950. Use this table to record your answers to parts 1 and 2 of this question. Part 1 then. Use the graph to find the number of deaths per 100,000 from typhoid in 1890 and 1945. Write these in the table. So we've got 1890 and 1945. So we've got 1890 and 1945 on the graph. So here we need to read up and across, and it's 25. And here we need to read up, across, and it's 2. Total number of deaths then from typhoid per year. Well, what you've got to remember here is that these are the number of deaths per 100,000. But 100,000 is not the population. If you had a population of 100,000, you would have 25 deaths. But we actually have a population of 4 million. So how many 100,000s are there in 4 million? And then times that number by 25. And you should come out with an answer of 1,000. If you do the same for 1945, you get a number of deaths of 160. And then you need both of these for that, and both of those for that. Okay, so that's that question. The next part of that question then starts asking you about this. Why is the graph plotted for the number of deaths per 100,000 people rather than the total number of deaths? The graph is easier to read because the numbers are smaller, so you can tell if the total deaths fell each year. Results could be misleading because of population changes. Data is collected every 5 years. A fair comparison can be made with other places. Now, what I'd like to draw your attention to is 2 and 2. Strangely, they're the same. So that means you've got to put 2 ticks. Don't put 3, don't put 1. If you only know one answer, tick another one. But, here, why would it be easier to read if the numbers were smaller? Are we sure that the numbers are smaller? Oh, yeah, but the difference between 25 and 160 isn't really that big, so I'm going to rule that one out. So you can tell if the number of if the total deaths fell each year. Well, yes, you could tell that, but is that a reason? So I'm going to put a question mark there. Results could be misleading because of population changes. Yes, we have different population changes. If you look at the first question, you had a population of 4 million versus 8 million. Data is collected every 5 years. Yes, but what does that have to do with anything? So I'm going to rule that out. And a fair comparison can be made with other places, yes. If every place is measured by 100,000, then you can compare city to city or country to country, which means that I'm going to rule that one out as well. Chlorination of drinking water in London began in 1901, suggests reasons why it took 50 years to stop deaths from typhoid in London. Well, what the question talks about right at the start is that it's spread by food and water. Water and food. Okay. Now what that means then is that chlorination of your water is only going to is only part of the story, isn't it? So what you could start talking about here is that typhoid is also spread by contaminated food, and this is where you need to get the marks. So chlorinating water will not prevent this. You can also talk about was all water chlorinated, or just some. And you might want to then talk about, well, what if there was a well? Did they chlorinate the well? No, they didn't. They chlorinated the mains water. But did every house have mains water? No, not in 1901. So where did they get their water from? They got it from a well down the road, like Mr. Biggs. It also would have tasted different. How many of you have tasted the swimming pool water? No, it's not very nice, is it? And okay, your drinking water now doesn't taste like that, but if you aren't used to our water, and if you go abroad to other countries, their water tastes very different to ours. And so chlorinated water would have tasted different to the population in 1901. Final question for here then. Traces of harmful chemicals are sometimes made when chlorine is added to water. Why is chlorine added to water, even though harmful chemicals may be made? And this is the risks versus benefits question. Put ticks next to the boxes to the two correct answers. 2 ticks, 2 marks. Even though harmful chemicals can be made. Okay, the benefits of using chlorine is very small. Well, I'm going to go, right, no, that's not it. Why would, if the benefit was very small, why would we use it in the first place? The risk from the harmful chemicals is very small. I'm going to go, yes. The risk has to be small, because if the risk was so large, why would we use it? Chlorine is a toxic chemical. Yes, it is. It was actually used as a war gas. But why would then that be a reason to use it? Most people believe chlorine is risk-free. I don't think people believe that, because these two are linked. If chlorine is a toxic chemical, chlorine can't be risk-free. And chlorine kills bacteria in the water supply. Yes. There's your 2 answers. One final thing I'd like to talk to you about is, if we go back to PVC for a second and we talk about phthalates, we've already drawn a very similar diagram to this, where we've got our polymer chains and we've got our plasticizers. And those plasticizers look something similar to here, and this is a phthalate ester. Phthalate or phthalic acid is drawn here, and most of the plasticizers we have are derivatives of phthalic acid. This is diethyl hexyl phthalate. Diethyl, this is an ethyl group. This is an ethyl group. This is a hexyl group. This then is your other hexyl group. Di meaning 2, ethyl, and hexyl phthalates. The reason I'm bringing that up is when we think about these phthalates, is there a chemical bond between the polymer and the plasticizer? No, there is not. There is no solid line. So if that's the case, if we compare then a plastic to a sponge takes up water, but the water is not bound to the sponge. You can squeeze it out. What then happens if you squeeze a plastic? Does the plasticizer come out? It might not stream out like your water from a sponge, but it does come out. So if it gets squeezed by a baby's mouth, where do we think that the phthalate is going to go? And do we think that is going to be good for that child? Phthalates are toxic. Is it going to be good to put these toxic chemicals into this child? No. Okay. So, quite a lot of the most toxic phthalates have actually been banned in children's toys, and certainly the most dangerous have been banned from toys of the size that can be put in a child's mouth. Others have been banned from all toys as well. But we still use those same banned phthalate esters, those same banned plasticizers in medical equipment. And the reason for this is because this piece of apparatus, this piece, these wires going in here, the nappy, that, these are all made of plastic that contains plasticizer. All of these blood bags are made of plastic that contains plasticizer. All of these tubes that go to the blood bags are made of plastic that contains plasticizer. And we've got a whole heap of other stuff down the bottom here. And the reason is there is no suitable alternative. And because there is no alternative, the risk of the leaching plasticizer is small in comparison to the benefits that those products give us. And that is what we have to think about when we're talking about chemicals. The risks versus the benefits. I will leave it there. I hope you've enjoyed the video. Until next time, bye.